our next speaker is Charles Yuan, and he's going to talk about programming abstractions for quantum linear algebra.
Great. Hi, everyone. I'm Charles. I'm from UW-Madison, and I'm really excited today to tell you about the work that we've been doing on linear algebra. So the setting of today's work is going to be talking about quantum computational linear algebra, by which I mean the ability of a quantum computer to deliver us all of these awesome advantages in domains that require solving linear systems, physical simulations, regression, differential equations, these kinds of linear algebraic tasks. Now, quantum algorithms are now known to solve a lot of these things very efficiently. What I think is really cool is that it actually goes even beyond those obviously linear algebraic applications. Much of our modern understanding of how quantum algorithms works is through linear algebra. Some of these cases are obvious. The HHL algorithm literally takes a matrix and inverts it. Some are a little bit more subtle. For example, simulation is all about taking a Hamiltonian A and computing its time evolution operator e to the minus IAT. And even more surprising places, for example, Martin et al. Show in their great paper on the grand unification of quantum algorithms that even things like Grover's algorithm for database search can be conceived of as a linear algebraic task. In this case, you're actually going to be taking a sign function of a matrix, which you can kind of think about as discriminating the cases that you are and are not looking for. Now, the thing that these quantum algorithms give us is, in appropriate settings, up to an exponential speedup over their classical equivalents. For example, the HHL algorithm here can solve a linear system, invert a matrix of dimension n by n, in time that is polylogarithmic in the dimension n, as compared to the best known classical algorithms, which take time polynomial in n. All right, so this is that exponential speedup. Now, why should quantum computers be so good at linear algebra? Well, it's because in some sense they are linear algebra, right? We all know that qubits, their underlying mathematical representation is as vectors of complex numbers. And correspondingly, our operations on qubits are unitary matrices that multiply on these vectors, right? So that's the basic intuition here. I want to get a little bit more into the story about these polylogarithmic complexities here. Because if you think about it, it's a little bit weird that you ought to be able to invert a matrix in less time than it takes to just iterate over all of the rows of that matrix. There's something very suspicious going on. And the answer is, of course, that a quantum algorithm will assume a different access model to your matrix, some kind of sparse or structured access to that matrix. And indeed, over the last decade or two, the theory community has been working really hard to understand when this is possible and when this is not possible. So for example, in 2019, there was this really powerful theorem by Yuan that showed that quantum algorithms that assume efficient access to arbitrary dense matrices can be dequantized into classical ones. So we don't expect that quantum speedup to actually be robust. On the other hand, in that same year, Gillian, Lowe, and other authors showed that for a big class of matrices that are comprised of these structured matrices like circulants, sparse matrices that only have a few entries per row, as well as combinations of these via algebraic operators, you are able to encode these efficiently into a quantum algorithm, and we're more confident that the quantum speedup will be robust. So this takes us then to the core problem that we have today. Here's an oversimplified illustrative example of how we're going to try to implement a quantum algorithm. Here, which is telling us that we're just going to take a matrix and invert it. What the algorithm will do, if you look at the paper, and again, this is oversimplified, but it'll take some sort of algebraic decomposition of that function of the matrix. Here it might look like this one. And then in turn, for all of these input matrices A, you're going to have to think about how to actually decompose that input into smaller matrices that could be individual unitary gates or smaller circuits that are provided to you as a black box circuit. All right? And then once you've done with that, you're going to need to actually turn it all the way into a quantum circuit program that can actually execute on the computer. So the claim that I'll make is this is actually a programming challenge. Right, the first problem that we're going to tackle today is solving this abstraction gap of going from an abstract mathematical representation of the matrices and the functions you want to compute in your algorithm to the actual circuit. And the claim that I will make is that you could use existing quantum programming languages to do this. You could take a language like Qiskit and use it to implement the individual logic gates that you would get out of reading these theory papers. But instead, maybe there's a better way. We developed a system in which you can actually just take the math, write it directly in terms of operators, here they're embedded in Python, and compile them automatically to this circuit. Now, setting aside the abstraction itself, there's also the question of efficiency. Given a circuit that we've produced, is there a way to shrink the number of qubits and logic gates as much as possible? Okay. The claim that I'll make here is that you could, once again, use off-the-shelf existing quantum circuit optimizers for generic circuits for this task, and you'll get a speed up of around 30% for these circuits. But again, maybe there's a better way. We can exploit the structure of these high-level programs that we're discovering here to get something that is closer to a 95% speed up. All right. So let me tell you about how we're doing this with a little bit more background. All right. So some definitions about how this linear algebra works. How does a quantum computer actually store and process these vectors and matrices? We just saw that qubits are vectors. Now, in general, we're going to want more interesting vectors than these two complex numbers. And for that, we're going to need a definition called amplitude encoding. All this is basically saying is that if I have an arbitrary vector in Rn, I can create a quantum state where the entries of that vector become the scaled amplitudes of this quantum state. All right. So this is the specification for how we take a vector and shove it into a bunch of qubits. What's the circuit implementation of this? Well, that's a more complicated story, okay? This task is usually called quantum state preparation in the literature. You can go to Google Scholar and find millions of results about how to do this for specific domains. It's still a pretty complicated open problem for a lot of vectors out there, but the good news is that this talk is going to work with pretty much any existing method for state preparation that you want, and so we're going to mostly set this question aside. The next question is about the matrices, right? Our unitary operators are matrices. How do we make it express all of the matrices that we would want in an algorithm? For that, we're going to use a theoretical construction called a block encoding. So here we're going to assume that we have an arbitrary matrix A, which is an R of n by n. And what we're going to do is embed it into the upper left block of a unitary matrix that I'm going to represent as B of A. All right, so what's going on here? The thing is that for an arbitrary matrix, it may not be unitary. Right? If it's not unitary, I have no obvious way of just writing down logic gates whose semantics equals that matrix. But we can still shove it into a corner of a matrix that is going to be unitary. That is possible as long as we take the original matrix A and rescale it by a factor alpha, which is called a subnormalization. That alpha needs to be big enough such that this upper left block is small enough such that the overall matrix is unitary. And in this notation, the dots are the other three blocks of the matrix, which can be arbitrary in principle, as long as this whole thing is unitary. Now, why do I want this block encoding? It's because it actually lets me do matrix vector multiplication. If I take a block encoding of A and I multiply it by a vector x, that's my input, along with some ancilla qubits, I get out this superposition, which has one of its branches equal to AX, the matrix vector product that I care about. There's also some chance that I get this bottom state. That's a failure state that I do not want. I can tell that it's failed because the ancilla qubits will not have been reset all to 0 on that branch. So in order to get the state that I do want, I need to perform post-selection. I repeat this whole process. I measure the ancilla qubits. I accept only when all my ancillas are equal to 0. How many iterations does that take? Well, that's of course proportional to something along the lines of that amplitude right there. Using oblivious amplitude amplification, I can do this in time O of alpha. The runtime of the program that enables me to produce the matrix of A is proportional to the value of this subnormalization. It's not just a mathematical trick. All right, so the good news is, from the theory literature, we have a lot of ways of actually taking our basic block encodings and combining them into interesting matrices we'll use in our algorithms. If you look at our full paper, we give you the actual circuit semantics for how to do this. I mean, I won't explain it in detail, but yeah, there are interesting ways of sequencing and parallelizing these circuits to give you all of these algebraic combinations. What I want to do instead is to skip ahead to an example. Here is a linear algebraic program that you might plausibly see in a quantum algorithm for simulation, where you've got like two particles and are trying to figure out how they're interacting with each other. So given this program, which will be the high-level input, our system, which is called Cobble, will automatically synthesize this circuit for it. If you stare at the circuit a little bit, you'll kind of get the idea of where the structure is coming from. You know, we've got our kind of tensor product here along the two particles. We've got this addition and subtraction, and as well as this big addition over the top. This is kind of recursive structure here going on. Now, one question we'd like to answer about this program is, how much does it actually cost at runtime? So there are two main factors here, the number of logic gates that we're going to execute in the circuit, and something else that we'll actually see shortly. So that first part, right, the number of gates in this circuit. We can build this recursive cost analysis of it that basically just says, okay, well, if I'm taking the linear combination of two matrices, then that's going to require all the gates I need to implement the first one, all the gates I need to implement the second one, plus some additional overhead. All right. Now, this overhead term just accounts for some extra gates that we're going to have around in that circuit. It's an implementation detail for the most part. We don't want to spend that much time thinking about it. And so one convenient thing we can do is, just like in the last talk, we can switch to a simpler cost model that only asks for the number of queries to the individual matrices in this system. So for example, here we really only care about the number of copies of x and y in the circuit. And the query cost, in this case, is just going to be the sum of the query costs of the individual matrices, and we'll not worry too much about that O of 1 term for this simplified analysis. Now, like I said, there is another component that we need to care about, which is the subnormalization. Subnormalization tells us the number of repetitions of the circuit that we need to perform in order for the final post-selection to be successful. And the theory literature, once again, actually tells us how to compute these subnormalizations. For example, the rule for a linear combination is that the subnormalization for the linear combination is the linear combination of the components with these lambdas, these coefficients here, absolute valued. That's kind of important, actually, to take their absolute value. OK, so as I just said, what subnormalization is doing is it's saying, well, for the actual computation, we need to repeat this circuit over and over again. Each instance of that circuit is going to take some number of queries. And so the total cost of the algorithm is going to be the product of the number of queries per circuit and the subnormalization, which is the number of copies of the circuit. We can compute the number of queries and the subnormalization basically recursively over the program. In this case, you can derive for that program that it takes 2.6 repetitions on expectation before your post-selection succeeds. All right, how do we reduce these costs and make the program more efficient? Here is a very simple technique that takes our example program and makes it more efficient. It's called sum fusion, and it essentially is just algebraically rewriting the program, combining like terms and all of that, so you get this simpler program. Right? Why is this program actually simpler and better at runtime? Well, it's because it corresponds to this shorter circuit. Right? There's only one addition going on. It is actually shorter. And not only is that the case, but also the subnormalization is smaller. I won't show that explicitly, but you can take these programs, do the computation here, and you can reduce the original big circuit, which is the total cost of 20.8, to this new circuit that has only cost 8. That's a pretty good improvement. All right. But I also want to talk a little bit about the limitations of that simple rewriting strategy. What if we have a more complex linear algebraic program, this one that I showed from the beginning of the talk? Okay, this is the circuit that it naively compiles to. Okay, it's got all of these A's and B's, and it's kind of sequencing them, multiplying them, doing all of that sort of stuff. We can once again just combine like terms. Right? If we do that, we get this algebraic simplification. It certainly looks a lot shorter. Right? And you might hope that this will directly compile to a shorter circuit as well. But here is a little bit of a question that I want to ask you. And this is just in a classical linear algebraic setting. If I want to compute something like the product of A plus B with itself, where A plus B are both matrices, how many matrix additions do we need to do this? That's a bit of a quiz question. The answer is that you should only need to do one. Right? You take A plus B, and then that's like a saved value, and you just multiply that by itself. One addition, one multiplication. All right, and similarly, what if I wanted to take a matrix A to the 128th power? What's the fewest number of multiplications that I need? I'll give you the answer, it's 7. You do exponentiation by squaring, right? A squared, A to the 4th, etc. You do that 7 times, you get A to the 128, right? And classical linear algebraic frameworks like PyTorch or whatever are basically going to use that trick of reusing like terms. But does that work in the quantum setting? Well, no, it doesn't. Okay, and if you have something like this, and you actually compile it to a circuit, you still wind up with a very long and complicated circuit. The reason is because for these block encodings of matrices, every instance of the matrix has to actually be represented as a gate in the circuit. You can't just say, well, I already have the matrix, I'm going to reuse it. That doesn't really make sense in this model. So even though the expression is shorter, the circuit is still long. We're going to need to do something more sophisticated, which is something that we call polynomial fusion. We're going to exploit the fact that not only are we just multiplying and adding matrices, it's actually computing a polynomial over the same base. We'll collect all of the coefficients into a list, and with this list, we will feed it into a theoretical construction called the quantum singular value transformation. Now, I do not have the 60 minutes that is necessary to explain the QSVT to you, but it's this operation that lets us get an efficient circuit that corresponds to a polynomial of a given matrix. There are some technical things that we need to do to make this work. Specifically, our contributions in this work include a type system that lets us check the hermeticity of the matrix to make sure the QSVT is applicable, to scale the coefficients of the polynomial, check its parity, invoke existing solvers like PyQSP to generate the phase angles in the circuit, and then produce the final output circuit. All the details are in our full preprint, but the bottom line is, when we do this, we can get a vastly more efficient circuit for these matrix polynomials that are more efficient not only in the number of queries to our matrices, but most importantly in the subnormalization. QSVT generally gives a much better subnormalization than our direct additions and multiplications. So, I barely have any time left. Let's fly through some of the details in the full preprint. One of the things that we do is give an explicit formal cost model for all of the programs in our language. So for every operator, we can actually formally compute the number of queries in the matrices, the subnormalization, the number of ancilla qubits that we're using. There's a surprisingly high amount of math going on here, but one of the most interesting aspects I want to point out is, as I said before, if you're going to compute polynomials by simply computing monomials and then adding and multiplying them together, the subnormalization that corresponds to is actually equal to the mathematical L1 norm of the polynomial. Whereas if you use QSVT, you're getting the L infinity norm of the polynomial. L infinity norms are no greater than L1 norms, and in an example like this one, can be significantly less. Essentially, you're getting a lot of sign cancellation behavior. Based on this cost model, you can actually start defining these optimizations. So for example, the sum fusion operation that I talked about earlier is just reassociating the way that you are summing these things up, right? Rather than taking two big sums over small matrices, we're just combining these coefficients together and doing fewer additions. Polynomial fusion is just recognizing patterns of sums of monomials and collecting all of those into lists so that we can pass it into the QSVT subroutine. This seems very simple. The reality is that the compiler actually requires a whole lot more inference rules to kind of make this whole mechanism work, but I won't talk too much about that. Instead, let's talk a little bit about how this thing performs in practice. We asked, for example, how good is our system at reducing the cost of matrix expressions that you would find in applications? So here we studied a couple of different applications from things like simulation, regression, things like this, and we show overall, I think, meaningful improvements on these applications. We also wanted to ask how good is this system at resource estimation of well-known quantum algorithms. So again, we implemented things like matrix inversion, Hamiltonian simulation, and we show in this case that QSVT is performing fairly well. What we're doing here is that we're generating some of the very first executable circuit implementations of these algorithms. And finally, okay, we've also done an evaluation here. We compiled everything to circuits, we evaluated against state-of-the-art circuit optimizers, and we're showing that we are tying or outperforming many of these existing tools. There are some nitty-gritty next steps that we can do here to kind of make the compiler better, but let's skip over that because I want to end this talk on the message of saying, I think we've got something really cool here in terms of what looks like a quantum version of eigen, something that lets you actually build linear algebra, program, and reason about it in an interesting way. I think that there's a potential here for a big stack of quantum linear algebra that takes these applications and make them more realistic, the way that things like NumPy, TVM, JAX actually work in classical computation. So if you'd like to talk more about how we can build this sort of infrastructure, please come ask questions. Thanks.
Thank you. So many of the applications in scientific computing already have, as you said, structured matrices, but also sparse matrices. Mm-hmm. But even then, something which goes from quadratic to linear.
Mm-hmm.
So what's the black magic? Like, how do you get all the way to, and also in the classical setting, there's so much optimization that's already been done by a lot of people with massive libraries taking advantage of the structure.
Yeah.
So what is the extra thing? I still don't get what's the extra stuff that you get and how you're able to.
The extra stuff in quantum algorithms or the extra stuff in our system specifically?
The extra stuff in quantum algorithms, but also how you are leveraging it to, in practice, to get what seems like 65% more.
Yeah, both of those are very deep questions, and I'll try to answer them very quickly. In quantum algorithms, the thing that you get is the ability to not explicitly represent your matrices as arrays of floating point numbers that you iterate over and try to skip as many blank spots as possible to exploit sparsity, which is what is being done in those classical ways. And instead, you have things like the QSVT, where you are natively computing a function of a matrix by approximating the inverse function of a matrix as a polynomial, and then for every term in that polynomial, you insert a copy of that matrix. That's not like a very intuitive definition compared to anything that we do in classical linear algebra, but I have to say that is just the fundamental difference in the input and the processing model. In our system, a lot of what we're aiming to do is automate that, take the structure in these applications and make it possible to take our high-level programmatic descriptions and lower them automatically to circuits. I mean, you could say that most of programming languages is about taking this kind of theory knowledge, mechanizing it, and automating it. I'd love to talk with you more about, how we can make these insights surface more as well.
Thank you.